I am now going to describe, as well as demonstrate, the equipment and process of Aqua Regia Gold Refining Unit with stepwise procedure and operation of the unit. The Aqua Regia unit is an engineered and a robust construction which is a user-friendly design as well as layout and can be installed in a small footprint area with all operations and control at one point location. The frontal portion of the unit shows the two reactors. One is the digesting vessel in which the Aqua Regia reaction takes place with gold alloy, whereas the second is gold precipitation reactor. There are graduated day tanks of acids, hydrochloric and nitric acid, from which acid feed to digesting vessel is monitored. There are condensers connected to reactors for acid recovery and contain gold losses. Two separate filters for silver chloride and gold. The entire operation is controlled via a single panel which operates the steam generator, scrubber pump, compressor, and chilling unit. The vent outlet of the condensers is commonly connected to the scrubber via pipe. The frontal portion also shows various valves with indicative instructions for liquid transfers and air purging in various steps. The access to the back is quite easy by a staircase and platform, where primarily the acid day tanks are monitored and gold alloy charging is done. In the gold precipitation tank, also reducing agent is charged from the back manually, as well as operation of automatic system is monitored from this side. The process starts by startup of pump and blower in the scrubber, which is done from the main panel board attached to the Aqua Regia unit. Once the pump is started, the circulation of scrubbing liquid, mainly caustic soda, is started. This ensures the safety towards absorption of NOx and acidic fumes generated during Aqua Regia and reduction processes. So also the compressor, steam generator, and chilling unit is activated from the main panel. Steam generation is ensured by the rising pressure of steam as indicated in the pressure indicator of main panel board. The chilling unit temperatures are also displayed on the indicator panel. The two pneumatic pumps for acid loading, HCI and nitric acid, are checked, whether their suction pipes are inside the acid storage tanks or carboys. The acid is then loaded, one after the other, in the graduated storage tanks by the way of push-button switch operation. This predetermined acid quantities are calculated on the basis of alloy composition and formulation calculation given by our professional engineers. Alloy gold flakes or grains are then loaded in the basket, fitted on the digesting vessel. The basket is either a stationary perforated basket for processing alloy with silver contents less than 10%, or a rotating perforated basket for processing alloy with silver contents up to maximum 15%. Then the hydrochloric acid valve is opened slowly and desired quantities of HCI are fed in the digesting vessel. After finishing HCI feeding, nitric acid transfer valve is opened so that it is fed in the digesting vessel. The quantities of these acids are predetermined and calculated as per the alloy composition of gold, silver, base metal, and other impurities. Upon completion of acid feeding, the Aqua Regia, which is mix acid, starts reacting straight away with the alloy, percolating through the perforations. The change in color is noticed where we can visualize the gold dissolving in acid. Steam is now started from the panel board, and we see live purging of steam entering inside the glass reactor. As time goes by, we see temperature indicator display on the panel board showing rise in temperature. The control loop of temperature is such that steam injection is cut off at 70 degrees centigrade and restarted at 66 degrees centigrade. These temperatures are adjustable. The optimum temperature, around 70 degrees centigrade, ensures better reaction and thereby better Aqua Regia efficiency. While the Aqua Regia reaction goes on, gold dissolves in the mix acid, whereas silver gets converted to silver chloride crystals, which are white in nature. These white crystals tend to formulate a surface or a shield around the alloy. Over a period of time, this shield covers the surface of the alloy, which restricts the percolation of aqua regia mix acid to attach the alloy. While processing alloys with lower silver content, this behavior, known as a shielding effect, retards the reaction time as well as reaction efficiency. Hence, at this stage, if it is a stationary basket, the operator needs to give jerks and shakes from time to time, which breaks up the shielding effect and alloys the surface of the alloy to be more open for the reaction. Time to time, also air purging is given to the digesting vessel by operating a valve on the frontal panel of the equipment. The shielding effect is well taken care of by our perforated rotating basket, as demonstrated here. The white crystals of silver chloride, which forms a surface on the alloy, experience a rubbing effect due to axial rotation of the perforated basket at slow speed. Hence, these crystals separate out from the surface of the alloy and break up further to pass through the perforations of the rotating basket. This phenomena leaves the alloy open for acid attack, which helps the advancement of reaction. There establishes a continuous equilibrium between silver chloride crystal formation, removal of the same, and exposure of fresh alloy surface to aqua regia mix acid. Due to this phenomena, coupled by heat, alloys with higher silver content can be produced with better reaction efficiency in the shortest possible time. The completion of reaction is visualized by accumulation of white silver chloride crystals and changing color of the acid mix, wherein gold is dissolved. It is also seen that reddish fumes of NOx gases generated tend to slow down, and one finds more or less no fumes generated at the completion of reaction. This is the point where air purging or agitation should be done for a few minutes to remove residual NOx in the reaction mass. Steam injection should be stopped at this moment, and reaction mass is allowed to cool by itself up to ambient temperatures. The filter for silver chloride is then checked and connected. The discharge valve, as per the indication on the front panel, is opened for circulation circuit within the filter and digesting vessel. The filter is connected with the discharge valve outlet of the digesting vessel, whose nozzle is ensure being fit inside the filter nozzle, which is then locked, and also the fumes outlet connections to the scrubber is ensured. Slowly the discharge valve is opened and then quickly opened completely. All the silver chloride crystals form a surface on the filter media. The airflow is started as per the indicator on the panel to activate the pneumatic pump attached to the filter. Soon we see the internal circulation within the digesting vessel and filter is started. As time goes on, the bed of silver chloride becomes thicker and better, so also clearing up the liquid mass in the digesting vessel. We see white crystals reducing in the reaction mass, which is recirculated. The liquid also looks transparent. At a particular stage, we find no crystals of silver chloride coming back in the digesting vessel. At this point, the bottom discharge valve is fully opened to ensure the entire liquid filled up in the filter. The pneumatic pump is then stopped. The digesting vessel is then washed with DM water from the top by means of spray nozzle, which ensures all silver chloride being washed and transferred to the filter. The recirculation valve is then closed and transfer valve to second reactor, which is the precipitation reactor, is opened. The pneumatic pump is then started so that clear gold chloride solution, free of silver chloride, is transferred to precipitation reactor. Once the entire gold chloride solution is transferred, the bed of silver chloride is washed with DM water by the spray nozzle provided near the filter. The washing is completely done to ensure that traces of gold chloride being also transferred to the precipitation vessel. After the complete transfer is done, the pneumatic pump is stopped and discharge valve is closed. In the precipitation reactor, sodium metabisulfite is added, mixed with water, either manually or by an automatic metabisulfite loading system. For the manual charging, it is done from the top manhole on the reactor, whereas for the automated system, the redox pH probe detects and indicates the pH, which has a digital process controller and activates the pump to charge the right quantity of metabisulfite solution. In both the cases, changing color of the solution is the best indication to finish the charging. At the end of the charging, yellowish, shining gold crystals are seen to be sedimenting at the bottom of the reactor, whereas the solution turns greenish-blue and transparent. Aeration is done from time to time to ensure proper agitation in the reactor so that reducing agent metabisulfite reaches entire mass to precipitate gold. The gold filter is cleaned up and washed before the start of operation. It is then ensured to adjust the discharge nozzle of precipitation reactor fitting in the gold filter and locked. Now the pneumatic filter pump discharge valve is ensured in an open recirculation mode from the front panel of the equipment. Once this is ensured, the precipitation discharge valve is slowly opened and simultaneously airflow is started to activate the pneumatic pump. This cycle of reactor liquid discharge, filtration, and recirculation ensures the formation of bed of precipitated gold. This bed formation increases as circulation proceeds, and solution gets more and more clearer as gold gets precipitated. Formation of bed enhances the filtration efficiency, acting as a filter aid in the process. At the end of entire gold being filtered, the liquid can be viewed as complete transparent, bluish to greenish, depending upon the other impurities present in the alloy. At this point, the solution is transferred to storage tanks for recoveries of other metals and wastewater treatment. The pure gold sand collected as a bed on the filter is washed with nitric acid, hot DM water, and then cold DM water thoroughly to ensure removal of final traces of impurities. The wash liquid is also collected in the tanks together with all wastewater for recoveries and treatment. The pure gold sand now in the filter is gold of 999.5 purity and is taken for further process of gold bar manufacturing.